Yes, walaikum assalam. Good afternoon. Um, Hello. Can you hear me properly? Okay. তোমরা সবাই জয়েন করছো? Have you guys joined? Should I start? I'll of course wait like 3 or 4 more minutes and then I'll start. So please join. Okay, Rodro, Shahryar, I want to take attendance today. ঠিক আছে, like I want to ensure যে তোমরা সবাই attentive আছো. So Rodro, Shahryar and Soma Saha. তোমার নাম কি? Soma Saha, who is this? So Rodro aso, Shahryar aso, and Soma Saha টাকে কিংশুক. Okay, so কিংশুক আছো. তারপর স্টুপিড জার্ক, তুমি কে বলো, নাম বলো. শাহরিয়ার আছো, রৌদ্র আছো, কিংশুক আছো, আর কে কে আছো একটু বলো. ওকে, তনয় আছো. স্টুপিড জার্ক ইজ তনয়. No, I won't keep it secret. Stupid jerk is তনয়. Sorry for ruining the fun. Okay, so তনয় আছো. ওকে, তো বাকিরা কোথায়? আনাফ, আরিফুর, মাহিন, রাফিন, রাহিম, রাহুল, রিফাউল, আরিয়ান, আনান, বিশাল. Where are you people? Let's see. There is a user account মানে নাম দেওয়া নাই. তুমি কে বলো, নাম বলো. কমেন্ট করো অথবা আমাকে মেসেঞ্জারে বলো, যে কোনো একটা. রাফিন আসছো, প্রেজেন্ট. আরিফুর প্রেজেন্ট. না, মাহিন doesn't use two accounts, সুবিচার কিস্তা নয়. আচ্ছা, Raffin present. Okay, so Raffin. Where's Raffin? Yes, Raffin. And then Arifur. ওকে, তো বাকি আছে কি আনাফ, মাহিন, তারপর রিফাউল। রিফাউল কি জানে না? স্যার কেন বললেন এটা ফান? হ্যাঁ, ফান, একটু ফান রুইন করলাম আর কি আজকে। ওকে, তো এখন আছো রাফিন, শাহরিয়ার, কিংসুক, তনয় আর আরিফুর। বাকিরা এখনো নাই। রিফাউল কোথায়? আমি মেনশন দিই তো। রিফাউলকে মেনশন দিলাম, তারপর আর কে এখনো আসে নাই? আনাফ, তারপর মাহিন। মাহিন এখনো আসে নাই। মাহিনের ফেসবুকে জানি কি অ্যাটম, প্রোটন, ইলেকট্রন। তারপরে আর কে? রাহিম। রাহিম কোনো ক্লাস করে না লাইভে, কেন? তারপর রাহুল। হ্যাঁ, আচ্ছা, থ্যাংক ইউ শাহরিয়ার। রাহুলকে মেনশন দিছো, রিফাল অলরেডি মেনশন হয়েছে। আরিয়ান, আনান, বিশাল। আরিয়ান, আনান, বিশাল। জয়েন। রাহুল জিজ্ঞেস করতেছে কি? ইন্টারনেট ইস্যুস আনাফের। আর হচ্ছে অ্যাটম, প্রোটন, ইলেকট্রনের খবর নাই। আর কারো? ওকে, তো ঠিক আছে, অনেকক্ষণ ওয়েট করলাম। রাফিন দিয়ে অ্যাকাউন্ট খুলছি, বাট আমি হলাম রোটন আহমেদ। রোটন আহমেদ কে রে ভাই? কি বলতো রাফিন? আম, আসসালামু আলাইকুম স্যার। হ্যাঁ, রিফাউল আসছো। তাহলে তোমার কমেন্টেটর হওয়া উচিত। কমেন্টেটর কেন? কি ইউটিউব স্ট্রিম করতেছি দেখে তারপরে এখন কি গেম রিভিউ শুরু করে দেব? তারপরে কমেন্টেটর? গেম রিভিউ করাই যায় তাই না? আজকে আজকে যেমন আমরা একটা আজকে আমরা একটা ইউটিউব ভিডিও রিভিউ করব। কোনো ইউবিলি ভিডিও না, আমরা একটা অ্যাস্ট্রোফিজিক্স এর ভিডিও রিভিউ করব। আচ্ছা, ওকে, সো লেটস বিগিন। ওকে, so we are starting now. So I'll start from here. So in the previous class we studied about Hubble's observation. So Hubble made what observation? You remember? Hubble made the observations of very distant galaxies, right? Very distant galaxies. How did he do that? By splitting their light into spectrum. And overall, he observed that light from the galaxies are redshifted, right? Which means an increase in wavelength, correct? So all galaxies are moving away from us. So these were our conclusions, that the light from distant galaxies are redshifted. So all galaxies are moving away from us. That was Hubble's conclusion, from which the more distant the galaxy, the faster it is moving away. So we can conclude that the universe is expanding. Absolutely no doubt about it. Great. After which, this is what we're going to say. Okay, this is the Big Bang Theory. Let me just put a title up there. Layout. Yeah, title. Yeah. This is the. I'm starting to talk about the Big Bang Theory. And so the redshift shows that the universe is expanding, right? Okay, so that much we know from Hubble's observations. Then that combined with general relativity. Now, what is general relativity? General relativity is Einstein's theory of gravity. General relativity is basically Einstein's theory of gravity. We don't need to go deep into that yet, okay? But we will just say this: that general relativity combined with the Big Bang theory predicted that the universe and time itself would begin in the Big Bang. So general relativity combined with the Big Bang theory, combined with the expansion of the universe, the fact that the universe is expanding, combined with the theory of general relativity developed by Einstein, the Big Bang theory was formed, and it predicted that the universe and time itself began in the Big Bang. So both the universe and time. So what do I mean by the universe and time itself? You see, we live in a space-time universe, basically, right? Like, if you want to describe your current state, you can say, I am I let's say I'll try to state my current state. Okay, I'll try to say my current state. So I am 3 feet away in my room. In my room, I want to say that I am 3 feet away from the, I think this is from the east wall. Okay, so I'm 3 feet away from the east wall. This is one coordinate, right? Let's call this x-axis. So I'm 3 feet away from the east wall, and I am 1 feet away from the south wall. So that's two coordinates, x, y. Okay, so I'm 3 feet away from the east wall, 1 feet away from the south wall. So that's two coordinates. Now you know that I am somewhere 1 feet away from the south wall and 3 feet away from the east wall. But I can be Spider-Man and be on the ceiling. I can be PewDiePie and be floor gang, or I can be sitting on a chair. So I say I am sitting on a chair, so I am about 1 feet above the floor. So you know precisely my position. You perfectly know my position right now. You know that I am 1 feet above the floor, and maybe I can say tell you that I am in 8th floor. So you know how many feet I am, how much far I am from the ground, and you know that I'm, if you know my, if my room is like the coordinate system, so you know my three, you know perfectly my position. All right. Now, however, another thing you need to know about me, because right now I am talking. In the previous moment I was silent, and in this moment I'm again talking. So only saying that I am at this position does not fully describe me. You also need to tell my time. Okay, so if I complete this saying that I am in this position and the time is 5:13 p.m. Bangladesh time, that completely defines my state, current state. But now it is 5:14 p.m. and now I'm in a completely different state. And I'm just talking in minutes, I can talk in seconds and milliseconds and nanoseconds. So you get the point. The idea is we live in x, y, z and time. We live in 4 dimensions. Okay, so space and time, x, y, z are space, and the clock, that's time. Okay, so when did space begin? Well, the Big Bang theory says that the 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 Big Bang theory says that all that is in the universe, that is everything, the entire space, including this room, which was some, at some point it was part of the ground because the building didn't exist. And before that, it was part of the sun because the earth wasn't formed, it was still being formed from the sun. And before that, it was part of a supernova because the sun was formed from the nebula of a supernova. And before that supernova, it was a star, it was a very big star. Before then, it was another nebula. Before then, it was, we don't really know. Interesting, isn't it? Okay, so I'll get to that. But the Big Bang Theory basically says that all that is in the universe was in one point. So it was all in one point. We call it the point of singularity. The point of singularity, like the everything that we see in the universe, all space and time, it was all in one single point, the point of singularity. And then from that point from which the universe inflated or inflated or expanded all the way up to its current state in the past 13.8 billion years. So the Big Bang Theory precisely says that the universe is now at this stage, but 13.8 billion years ago, all of this space was at a single point, and Einstein's theory of general relativity says that that point was the starting of time itself. Okay? But we don't need to go there, we just need to understand that all of it began from a single point, the Big Bang Theory. Cool. Single point. 13.8 billion years ago. Alright. Now, what's the evidence? What is the evidence that will lead me to believe that indeed the Big Bang Theory is correct? So, what's the evidence backing up the Big Bang Theory? Well, the evidence is that according to the theory, so here's how you prove a theory. For example, I tell you Newton's theory of force, mass, and acceleration. F is equal to ma. What's the evidence? Well, you apply a 1 Newton force to a 1 kg object and you see that indeed the object accelerates at 1 meter per second square. So the formula works out. F is equal to ma works out. You repeat it with many other cases and it always works out. F is equal to ma always works out. So yes, that theory is validated. So the Big Bang Theory, what's the evidence backing up the Big Bang Theory? Well, the Big Bang Theory predicts, just like F equal to ma predicts that if you apply a 1 Newton force to a 1 kg mass, it will accelerate at 1 meter per second square. Similarly, the Big Bang Theory predicts that at the initial stage, the temperature would be as high as 10 billion Kelvin. So according to the Big Bang Theory, at the initial stage, that is the single point, the point of singularity, near that stage, the temperature would be as high as 10 billion Kelvin, consisting of nothing but protons, neutrons, and electrons. So Big Bang Theory states that there was an initial stage that was very, very small point, and at that initial stage, it was very hot, that is 10 billion Kelvin temperature. Now you may ask, why? Why does the theory predict that? Well, think about it. Let's think about it. Think about the entire universe. Do you think there is a lot of energy in the universe or very little energy? We talked about supernova, we talked about subatomic particle fusion, we talked about nuclear fusion, we talked about, and so we talked about all the stars. So you can clearly see there's a huge amount of energy in the entire universe, right? So if all of that energy is crunched up into a very small space, into a very small point, that point will definitely be very, very high temperature, correct? So does that make sense? So that is why, by some calculations, the Big Bang Theory actually predicts that the temperature would be as high as 10 billion Kelvin. You with me so far? Clear so far? Great. Now, Okay. Any questions so far before I get to the next point? Any questions up to that? The point that the Big Bang Theory predicts that the temperature will be very, very high. Let me go through your comments. So, how time is formed? What are the requirements of time? Well, time is formed with space. We don't know how, just like we don't know how space was formed. I'll get to what we know and what we don't know. Today's class will mostly be about that, what we know and what we don't know. I'll explain that video. And so, time, how was time formed and how was space formed? We don't know, but that's a very good question. Space time. The further somebody travels to space, the slower he is experiencing time, seeing time because he is moving away from it. Not from you. Well, not the further. It's modify your statement with the faster, and it makes sense. The faster somebody travels in space, through space, the slower he's experiencing time. Cause he is cause I will explain the cause will be explained in another video that I gave you the link to refold. It's why we can't go faster than speed of light. Anyway, so can you hold on? How did we measure the temperature? No, we definitely did not say that we measured 10 billion Kelvin temperature. We just said the theory predicts, just like F is equal to ma predicts that the acceleration will be 1 meter per second square. And then we go and measure that acceleration and we find that it's actually 1 meter per second square. But in this case, we don't actually go and measure the temperature. What we do is the next 2 points. Okay? Yes, everything was in a very small space called during the start of the universe. From there, we had the Big Bang. You believe in your review, Chai? Did you watch the latest one, Rafen? If you haven't, you must check it out. It's really fun. Sir, why is it impossible to stop or freeze time? That's a very good question. But here's the thing. Well, think about it for some days. Think about it. What will happen if you freeze time? Just try to think about it and you will see that it doesn't make sense. That it just doesn't make sense. Like, nothing works. You can't freeze time. Like, think about it for a few minutes and you'll get it. Like, it doesn't make sense. You just gotta think about it. Okay. Alright, so let's get to the next point. According to the theory, at the initial stage, the temperature should be very high, like 10 billion Kelvin. Now, here's the thing about high temperature. You guys remember stars? Why do stars emit light of different colors? Because of their temperatures. So, different stars emit different colors of light because they have different surface temperatures, right? For example, the sun is at a surface temperature of about 5,000 5,000 Kelvin, somewhere around there, 5,000 6,000 Kelvin. So it emits yellow light. But another star which is maybe very, very high temperature, like 30,000 Kelvin, that emits blue light. Now, notice the pattern. Here's a spectrum for your observation. Like, okay, no, I'm actually gonna let me bring up an electromagnetic spectrum here. Okay, so I'll copy this image and let me just paste it here. Hello. Hi. Hi. So yeah, this is what I wanted to show you. So you see, this is the electromagnetic spectrum. So at the bottom of the spectrum, the very low frequency, you can see the radio waves and the television waves, that is basically radio waves, and the microwaves. Also, you can call them the radar waves because radars use microwaves. And then you have infrared, and then you have a very small spectrum which we call the visible light, that is the some frequencies of the electromagnetic spectrum that are visible to us, and that is the visible light, and then ultraviolet, x-ray, gamma ray. Now observe this, the sun's color is yellow, right? And a low temperature stars are red, medium temperature stars are yellow, very high temperature stars are blue. So what do you think a temperature that that is even higher than the temperature of the blue supergiant stars, what color that temperature object, if any object has a temperature that is higher than 30,000 Kelvin, that will definitely still emit electromagnetic radiation, but it will be even higher frequency than blue light. Does that make sense? Let me repeat that. The sun has a surface temperature of about 6,000 Kelvin, right? And it emits yellow light. The other stars, the red giants, they have lower temperature and they emit red light. So that's a lower frequency. Yellow is a higher frequency. And then stars that have much higher temperature, such as 30,000 Kelvin, those stars emit blue light, correct? So the higher the temperature of the star, the higher the frequency of light that it emits. Does that make sense? High temperature stars emit light of high frequency. Get it? High temperature stars emit light of higher frequencies. So any high temperature object, that is not just true for stars, that is true for any objects. So if any object has 30,000 Kelvin temperature, it will emit blue light. But if the temperature goes beyond 30,000 Kelvin, it will emit violet light. But what if the temperature goes even beyond that, maybe 70,000 Kelvin? Then it will not anymore emit visible light from the electromagnetic spectrum. It will emit light of even higher frequency than the visible spectrum. So it will emit ultraviolet light. Ultraviolet light, you understand? So we say that there is red light, yellow light, blue light, green light, but actually these are just the light waves that we can see. These are just the light waves that are within the range of the electromagnetic spectrum, the very small range of the electromagnetic spectrum that is visible to us. There are lots of other light rays that are not directly visible to our eyes, such as infrared, the ray that you use to turn on your TV or your air conditioner. There is ultraviolet light, the ray that you use if you check for forged notes, like Jaltaka, you know. So when you check for forged notes, you actually use ultraviolet light. Okay, and then there are X-rays that you use in hospitals. That's also light. It's just light that you can't see because it has very high frequency. Gamma rays, again, you use to treat cancer, but those are also light, but those are beyond the frequency that we can see. These are frequencies that we cannot see. Only these are the frequencies that we can see directly with our eyes. Anyway, now, so what you understand by now is that the higher the temperature of an object, the higher the frequency of light that it emits. So something that has an even higher temperature will emit either ultraviolet light, or something that has even higher will emit X-rays, something that has even higher will emit gamma rays. So now let's get to the 10 billion Kelvin temperature. This temperature object, an object that has a temperature of 10 billion Kelvin, it will definitely emit a lot of electromagnetic waves, but those electromagnetic waves will have a very high frequency, right? So the highly concentrated matter at such high temperature, as it exploded, must have emitted light, right? And this light of very high frequency must have emitted light of very high frequency. Does this point make sense? If something is very much hot, like 10 billion Kelvin temperature, it will emit light but of very high frequency, correct? Any questions so far? Okay, so you asked how waves travel in space, do they collide with planets? Yes, of course. Violet, yes. So you answered violet, yes, and then yes, can it emit gamma ray? Yes, it can emit gamma ray. That means there are stars that emit gamma rays. No, they're not. There are not stars. Well, stars do emit gamma rays, but small amount, small amount. But if the temperature was this high, 10 billion Kelvin, this was only the case when the universe was at a single point. Okay, this has never been this case. 10 billion Kelvin temperature has never, you can never see it in the universe. It was only this hot at the very beginning. Okay, so you're telling me gamma rays have color, just we can't see it. Very good question. We actually can't see gamma rays, so we don't say that they have any color. Actually, light has some, the light we can see it, so different wavelengths of light, we just gave it different names of colors for us to make life easy for us. Instead of saying, hey, that car is red, I could say, hey, that car is absorbing, that car is reflecting 700 nanometer electromagnetic waves. You get it? Like saying, hey, that car is red, and saying, hey, that car is reflecting 700 nanometer wavelength electromagnetic waves is the same thing. Is the same thing. Okay? Or, hey, that car is blue. Or you can say, hey, that car is reflecting 300 to 400 nanometer wavelength electromagnetic waves. So there you have it. That's color. That's color. Color is nothing but wavelength and frequency. How we use ultraviolet to check forged notes. So how do we use it? It's just that there is a line in real notes that that is drawn with something that that only shines when ultraviolet light is shown over it. So real banknotes will show a line when ultraviolet light is given on them, but forged notes will not. So that. That's just random facts for you. Okay. Sun also emits UV rays. That means sun is also that much hot. Sun emits UV rays of very small amount compared to yellow. Sun emits most of its light as yellow light. It emits all the electromagnetic waves, but most of it, the majority, okay, the majority is yellow. So for a star that is higher temperature, the majority is blue. For some object that is even more higher temperature, that doesn't exist in the solar system, right, in the universe right now, but existed at the big bang, that is 10 billion Kelvin temperature, that object will mostly emit gamma rays and gamma rays only, because very high frequency light, because they are at very high temperature. People will beat me. Can't we not draw that? Um, what? I'm not sure what you mean. Please ask that question again. Okay, so I think you understand the frequency part. Now, here's the thing. It's light, right? I mean, it's gamma rays, fine. So that gamma ray, think about it. Think about it like this. Um, you have a football, okay, and you have you punctured that football. Very sad life. But then you put some bricks inside it, some one small little brick inside it, okay, and then you pump that ball up and you fix that puncture. So now it's again a football, right? However, that football, although it's now bigger than the original punctured football, the bigger football still has that little brick inside it, right? It still has that little brick inside it. Now apply that similar analogy to the universe. The universe was at a very small space and it was emitting light, right? Because it was very hot, so it was emitting gamma rays. And then it expanded into this huge universe. But all over this huge universe, there should be some remnants of that light, the light from the beginning of the universe. You should be able to see that light all around you, everywhere you look. Anywhere you look in the universe, you should be able to see some gamma rays that have come straight from the time of the Big Bang. It should be there, right? Well, it should be there if the Big Bang theory is correct. And the truth is, yes, it is indeed there. That light from the explosion is indeed visible to us even today. We can directly see it. Okay? And it is indeed as cosmic microwave background radiation. Okay? Now here's a tricky question. We were talking about gamma rays, right? Very high frequency. But microwaves are very low frequency, even lower than visible light. Microwaves are very low frequency, gamma rays are very high frequency. So everywhere we look in the universe, we are supposed to see what? Gamma rays. But we actually see what? Microwaves all around us. But this microwave is actually that gamma ray. How? That's magical. The Doppler effect. Let me explain. As the universe expanded, think about this like this. You have a wave inside that small tiny universe. Okay? Now understand, when the universe expands, that wave, if you think about a wave, that wave has a wavelength, right? Crest to crest, trough to trough, peak to peak. The peak to peak distance, right? Now, if space expands, that is, if the universe, the space in the universe grows like a fabric, if the universe, the space itself grows bigger and bigger, if the universe expands, the distance between the one peak and another peak of that wave, that distance will also increase, isn't it? Because all the space in the universe is expanding. So that distance between peak to peak of each wave will also increase, because that wave is from the time of the Big Bang, right? So that wave's wavelength will increase. So the wavelength, hear me out here, the wavelength of this light increased, okay? And so the wavelength became longer and longer, all the way up to microwave today. Again, let me explain how microwave comes out. You see this graph, this frequency? 10 to the power 25 hertz is the frequency of gamma rays, whereas the frequency of microwaves is only 10 to the power 10 hertz. What about wavelength? The gamma rays have a wavelength very, very small, 10 to the power minus 15 centimeters. 10 to the power minus 15 centimeters. But the microwaves have wavelengths of about 1 centimeter. 10 to the power minus 15 and 1. So that's 1000 billion times. No, sorry, 1 million billion times. Right? Yes, 9 plus 6 is 15. Yes, 1 million billion times. Now, guess what? The universe expanded from that small size to its current state. Correct? And also, the size of the microwave. Oh, sorry, you're having buffering. Okay, I hope it's all right again. Sorry. All right, so now that we are back online, as I was saying, so you have to understand the wavelength was very, very small at one point at the beginning of the universe because it was at a very small space, right? Now, as the space expanded, the wavelength increased from 10 to the power minus 15 to 1 centimeter. That is why the microwave that we see all around us today, everywhere in the universe, you point your telescope up at the sky, you see some microwaves. Well, you don't actually see microwaves with a telescope. You actually see microwaves using a radio receiver. But yeah, the idea is the same. You point a radar at the sky, at the universe, at any direction you want, any direction, and you get the same intensity microwave. And if you make a calculation, you can predict that if this microwave existed back then, if this microwave had have really come from a very a large from a very long Doppler effect, stretching of wave from a very small space to this space, and then so if you make the calculation that how small this microwave actually was, you get the calculation that it was very, very small as a gamma ray, as small it was as small a wavelength as that will be emitted from a source of 10 billion Kelvin. Now understand this. Exactly, I'm trying to answer this question. Now, how do we know that this microwave is indeed from the Big Bang? Its intensity is so low that it is as if coming from a source of temperature of only 2.7 Kelvin, which does not make sense. There is nothing in the universe whose temperature is 2.7 Kelvin. I mean, there are some objects in the lab, but what I'm trying to say is up in the universe, in the empty space, all around us, we are not surrounded by some objects of temperature 2.7 Kelvin. No. If you look at the sky, there are no very cold objects. It's not like there are 2.7 Kelvin objects all around us. No. Then why is the intensity corresponding to 2.7 Kelvin? Because it's not actually from the 2.7 Kelvin object. It's not actually from any 2.7 Kelvin. There are no 2.7 Kelvin objects. So it is not from any object that exists now, it is indeed the stretched out light from the very beginning of the universe. And that's how, from the cosmic microwave background radiation and from the redshift, that the universe is still expanding, it has been expanding, we have evidence that indeed the Big Bang theory is the correct theory about the expansion and starting of the universe. So yes, the universe. Rafin, very good meme. Very good meme. Red to 700 nanometer electromagnetic wave, yeah. Okay. Okay. Anyway, so it is indeed the stretched out light from the very beginning of the universe. Okay? So that's what we know about the cosmic microwave background radiation. Any questions so far? And I will try to explain again what we know and what we don't know from Professor Dr. Lincoln's video, Don Lincoln's video in the next few minutes. Okay. So your questions are sun I've also already answered these. Sir, why higher temperature results more waves? Not more waves, higher temperature results higher frequency waves. That is because higher temperature means higher energy, and higher energy means higher energetic emission of light waves, and those light waves are higher frequency. The greater the frequency of light, the more its energy per photon. We will study this in more detail in the future, but that's the thing. Higher frequency light have higher energy. That's what. Very good question. If we say that nanometer, answer my question. Why would you know? Mohanlisa Mahin, what was your question, Mahin? Are ultra hot stars invisible? Um, no. Like invisible to the human eye, sure, but actually they're, to at least to my knowledge and as far as I've read, I'm pretty sure about this, there are no stars that have temperatures so high that they mostly emit other colors, such as that they mostly emit gamma rays. No, there are not the highest temperature stars that we know of are around 30,000 Kelvin, and so they emit blue light. Very good question. I'm sorry that I missed it. So if we say that nanometer, no, okay, I already answered it. Already answered. If a star just emits higher frequency of electromagnetic light, just camera, it will not be seen, right? Yes, but like I said, stars don't just emit gamma rays. Stars emit all the waves of the electromagnetic spectrum. But yes, if there was a star like that, hypothetically, yes, that will be invisible. Very good question. So is time as old as universe? Good question. To the best of our knowledge, as far as we know, probably time began with the universe. I'll get to what we know and what we don't know in a few minutes. Stay tuned for that. That's really cool stuff. So if there is gamma all around us, so where, yeah, exactly, there are not actually gamma. I predicted that there should be gamma, but actually there shouldn't be gamma because the gamma has expanded to microwave. So yeah, be clear about that. Actually, there is no gamma all around us. There is microwave around us because that gamma has expanded into microwave today. Every frequency is made from that one. No, not every. No, not like that. Good question, but that's not what we're not talking about. Um, what we are say like we're just talking about this particular microwave radiation. This particular microwave radiation comes from the point of singularity, the Big Bang. Other radiations just come from other sources. We have all sorts of radiation. Your television's screen, the phone you're watching right now, it is emitting visible light radiation. That doesn't come from the Big Bang. That doesn't come from anywhere. So yeah, look, no, just the cosmic microwave background radiation. Okay, very good question. White noise, also known as the what we see in the TV when the dish goes out, when the dish goes out, and basically when you can't find a signal, basically the what is a television? Let's answer that question. But what is a television? What does it do? It is connected ultimately to a radar. That radar is receiving signals from satellites, and those signals from satellites, they are microwaves, but they are some specific microwaves containing some information about the video that you're going to see in the television, and that's how you see what's in the television. Very simple. But what happens when maybe your radar is a little bit shifted? It's not at the correct position, it's not at the correct angle. Then you're not anymore receiving light, or sorry, microwave, which is also light but low frequency. So you're receiving microwave not anymore from the satellite. You're not anymore receiving the microwave from the satellite. You're missing the satellite. So what are you actually getting? What you're actually getting is the cosmic microwave background radiation, because that's the only signal that exists all around us, all around the universe, everywhere. The same intensity, the same radiation. So when the dish goes out and you see some white noise in the television screen, that white noise is actually cosmic microwave background radiation. Something to think about. Okay. Sir, so we can receive random microwaves? Yes, we receive random microwave. We can receive other microwaves, no problem, but this microwave, this particular microwave, we're talking about the cosmic microwave background radiation. Oh, sorry about that. Sir, so we can receive random microwaves? Acha, the ones. So the gamma ray to microwave. Yes, the gamma ray became microwave because the universe expanded, so the wavelength of this light increased longer and longer, all the way up to microwave today. Once that waves were visible. Yes, once this wave was also directly visible. Yes, definitely. In fact, the universe, this is a very fun, I love this topic. The entire universe at one point was orange. The entire universe was orange. There was just orange light all around the universe. Because the expansion that we're going to talk about in a bit, it actually happened first a very quick expansion, and then at a steady rate of expansion, at a steadily accelerating rate of expansion that is happening now. But it went from very tiny gamma ray very quickly to orange light, and then the universe was orange for a very long time. So everywhere you look there will be orange light, but that universe was very very small. There were only electrons whizzing around and photons, only electrons and photons at that point. That was very very long ago. That was 400,000 years ago. That's from where the cosmic microwave background radiation is, because it was all just it was all just a random orange light, and then that orange light eventually expanded and became this microwave today. Okay, so next question is what? Actually, what is time? Very good question. What is time? Something to think about. So, why microwaves harmless? Microwaves don't harm us unless it's in very high radiation. Okay, unless it's very high intensity. Microwaves only harm us if it's very high intensity, such as the microwave oven. Like your phone is constantly emitting microwaves to receive signals from your Wi-Fi, to communicate with your satellites, to communicate with your internet provider. Your phone is your SIM is constantly receiving and emitting microwaves. but that doesn't harm us. That's very small intensity. Only high intensity microwaves can harm us, such as the microwave oven. If you go and sit inside the microwave oven, then that will harm you. Don't try at home. Because it is observed by our water heats up. Yeah. Okay. Universe শুধু কমলা ছিল কেন apple orange color, I mean. So CMBR was orange. Yes, CMBR was orange at that point. CMBR জন্য কি? Cosmic microwave background radiation, what we're talking about. Okay, now let's get to one of the favorite YouTube videos that I've watched in a pretty long time. Let's get to it. Let's just jump into it. I love saying this. Okay, so we're gonna start from here. Okay, so let me play this. Let me know if
Question
you
of how
can
the
hear
universe
it.
began, mulled by generations of deep thinkers, is the question of how the universe began. And we know a great deal about what happened. Science offers a compelling and solid narrative for a great deal of the story, but it's not complete. Let me recap what we know for sure.
Okay, so let me just repeat what you said. Basically, um, it has been the one of the oldest mysteries is how the universe began, and science has given us a lot of more information about how it actually began, but the story is still not complete. And here is what we know. Okay, here's what we know for sure. All right. Floor gang. Not the speed to or not. Temperature is the speed of particles. So point of singularity or temperature. Well, point of singularity the time ছিল না বলি নাই আমি বলছি the time I didn't say that point of singularity time didn't exist. I said time started from the point of singularity. Okay, so there's a pretty big difference there. All right, now let's play. I have turned on the captions so that you can read it. Focus on the captions if you can't hear it. That's all right. I think if I can maybe. Uh, Never mind. Okay. So
We know that the visible universe was once smaller and hotter, and it's expanding.
So we know that the visible universe was once smaller and hotter, and it's expanding. Like I said, 10 billion Kelvin temperatures. We know that that's for sure because that's what we get from SCMBR.
We know that there was a moment when the expansion began.
We know that there was a moment when the expansion began. All right. So like at some particular moment, the universe started to expand. We know that.
We know that that moment
We know that that moment was about 13.8 billion years ago. No doubt about it. 13.8 billion years ago, the universe started to expand.
was about 13.8 billion years ago. For over 50 years, we've known of the cosmic microwave background radiation.
For over 50 years, we have known of the cosmic microwave background radiation. So yes, the cosmic microwave background radiation, the CMBR that we just studied, it was first discovered using this radar that you can see, and it was discovered about 50 years ago. So this is known information for the past 50 years.
Which is also called the CMB.
Which is also called the CMB. And just like this, the CMB has
The
same
CMB is the
radiation.
earliest thing we can see in the history.
The CMB is the earliest thing we can see in the history of the universe. Okay, so it's the earliest thing that we can see. There's nothing we can see directly that's older than the CMB, the cosmic microwave background radiation.
History of the universe. In fact, it's the remnant afterglow of when the universe began.
It's the remnant afterglow of when the universe began. Okay, so remnant afterglow. Is there a problem? Oh. I said time started at the point of singularity. As far as we know, time started at the point of singularity. So when something starts, does it exist? Yes. But does it exist before that? Well, there is nothing before the starting of time. I'll get to that later, okay? Let's talk about time later. Just focus on the content right now.
The CMB presents a picture of when the universe was about 400,000 years.
Okay, so the CMB presents a picture of when the universe was about 400,000 years old. Now 400,000 sounds like very old universe, right? The universe is very old. 400,000 years have passed since its creation, as far as we know. So 400,000 years, but when compared to 13.8 billion years, 400,000 years is nothing, right? Okay.
Years old, which is when the universe was about 0.003% its current age. If we equate my current age to the age of the universe, seeing this.
Okay, that's just a fun analogy. If we equate his current age, not mine, his current age to the age of the universe, so he's like, I don't know, maybe 50, 60 right now. So seeing the CMB is
CMB
like
is like seeing a baby picture of me when I was 14 hours old.
when he was 14 hours old. So you can compare the analogy. Okay, that's just an analogy, like percentage wise. Like this is when the universe was 0.03% of its current age.
Man, I was a cute baby.
Yeah, okay.
However, while the oldest thing we can literally see existed 400,000 years after the.
So this is something to think about, okay? The oldest thing that we can literally see, because we can literally see the cosmic microwave background radiation using radar. But the oldest thing that we can see literally existed 400,000 years after the universe actually began.
The universe began, we actually know about the conditions in the universe much, much before.
So, but however, due to some really good experiments in the CERN laboratories and in the Fermi laboratories, the particle physics laboratories, the astrophysics laboratories, for due to those experiments, we actually know about the conditions in the universe much before that time. Okay, much before that time. All right.
That time. For instance, at the moment which we can see the CMB, the universe had a temperature of about 2,700 degrees centigrade.
Okay, so at the moment that we see the CMB, the temperature was about 2700 degrees Celsius. So if you can compare it, it's only about 3000 Kelvin. So that if you compare it, it's about orange light. Like I said, orange light. So at the moment we see the CMB, if you compare it to the beginning of the universe, it was 3000 Kelvin, 2700 degrees Celsius. So that's not the 10 billion Kelvin that we predicted, right? But by doing some experiments in the lab, we can see that the initial conditions were like 10 billion kelvins. We'll get to
But
that.
the universe is expanding and cooling off.
This is very important. Let me just repeat that.
700 degrees centigrade. But the universe.
But the universe is expanding and cooling off. So the more the universe expands, the more it cools down. Okay, because more the more the universe expands, that means the same amount of energy is being distributed over a larger space, and the more empty space there is, the lower the temperature overall of the universe. Okay, you asked a question. I'll answer a question, few questions. Yeah. um or what? Here's a lazy guy. What was your question, Tonoy? What was your question? I can't see your question. You didn't ask any question. You just said I asked a question. Okay, anyway, please repeat your question. CMB hurts my eyes. No.
universe is expanding and cooling off. At even earlier times, the universe was hotter than that.
At even earlier times, the universe was hotter than that. Okay, so hotter than 3000 Kelvin.
Well, we can't see the universe when it was much hotter. We routinely
So this is a video of actually the Large Hadron Collider. It's a very famous collider in the CERN laboratories and in the Fermi laboratories. So these are very long colliders. What they do is they accelerate particles at very high speed, like protons and electrons. They accelerate them at very high speed and they make them collide. And when those particles collide for very short amount of time, they create scenarios of temperature much higher than 3000 Kelvin. They create scenarios of temperatures about near 10 billion Kelvin, which is for a very brief moment of time they do create those insanely high temperatures, which recreates the scenario of what it was like during the Big Bang. So that's how, even though the actually we can only see up to the CMB, which existed only 400,000 years after the Big Bang, but thanks to these experiments, we do know more about even what happened even before then, when the universe was much hotter.
Well, we can't see the universe when it was much hotter.
Well, while we can see the universe when it was much hotter, we
We
routinely
routinely recreate the conditions of the early universe in huge particle accelerators like the Large Hadron Collider in Europe. When we smash nuclei of lead together,
So when we smash nuclei of lead together, like these are nuclei of lead smashing into each other. The temperatures are as high as
the temperatures are as high as 7 trillion degrees centigrade.
So
one has to be a little more careful about the.
So 7 trillion degrees Celsius. That's about 10 billion Kelvin, right? If you do the math, I think no, that's actually greater than 10 billion Kelvin. So yes, near the conditions of the starting of the universe.
Definition of temperature when talking about the most energetic collisions ever made. But when the LHC is colliding beams of protons, researchers create temperatures last common in the universe when it was a tenth of a trillionth of a second old.
So this is very important. So when they make protons collide, they have been able to create temperatures that correspond to the same temperature or same scenario that the universe was when it was 1 trillionth of a second old. 1 trillionth of a second old. So that's the really the beginning. That's really very near the beginning. 1 trillionth of a second. Imagine the age of the universe. 1 trillionth of a second. So that's 10 to the power minus 13
That's
seconds.
10 to the minus 13 seconds for the amateur scientist crowd.
Okay, so 10 to the power minus 13 seconds. When the age of the universe was 10 to the power minus 13 seconds, that scenario is recreated in the Large Hadron Collider when they collide protons. Very exciting stuff. So what? Okay, you have questions. We do not need a if the universe cools down as it expands, then why the Earth is becoming hotter? Okay, the universe cools down as it expands. That is because the empty space is increasing. So the average average temperature of the entire universe is decreasing. However, that is happening at an extremely slow rate compared to maybe our temperature, Earth's temperature. That's really ridiculous comparison, okay? Because uh, the Earth has very high temperature and the average temperature of the universe is only about 4 Kelvin or near about 4 Kelvin. So the average temperature of the universe doesn't compare to the temperature of each object because these objects are really small. The Earth is extremely small compared to the universe. Will a time come when the universe gets completely cooked down? I'm not sure what you mean by cooked down. Please repeat. Will the universe end up by freezing? We don't know. We can only speculate. Before 65 million years, there was 23 hour a day, and now 24 hour a day, and 100 minute a year. There will be 100 million year. There will be 25 hour a day. Is it true? And if it's true, why it will happen? It can happen because the space between, as the universe is expanding, even the space between the sun and the earth is expanding at a very very small rate, but it is expanding. So it is gonna take in 100 million year. Yes, sure, that will happen. But will the earth exist in 100 million year? I think no, because the sun will already become a red giant and gobble up the earth. So no. All right, moving on.
So these are all facts. If we define the moment when the expansion of the universe began to be time equals 0,
Now here this one really uh, focus here. If we define the moment when the expansion of the universe began to be time equals 0, like when the expansion began, if when the expansion began is time equals 0,
we have hard data for times after 10 to the minus 13 seconds.
we have hard data, like we have solid data, evidence, experiments for everything that happened after 10 to the power minus 13 seconds, and so on. So 10 after 10 to the power minus 13 seconds to present day, we have hard data about it.
That should impress the heck out of you. It still blows my mind, and it's what I do every day.
It's actually really impressive.
But for all we know, there are still things we don't. For instance, there is that time period between time equals 0 and 10 to the minus 13 seconds.
So check this out. This is very interesting. This is the diagram that I have in my slide. So if this is time equals 0 and this is present day today, and this is 1 billion years, 400,000 years, like 1 billion years after the creation of the universe, 400,000 years after the creation of the universe, this is from where we get the CMB, when the particles have formed and it's orange light and all that thing. This is near 3 minutes since the universe started expanding. This is 10 to the power minus 13 seconds since the universe started expanding. But before that, from 0 second to 10 to the power minus 13 second, we have no idea what happened. Okay?
Science doesn't know exactly what happened during that time. And we don't know about time equals 0, and even less about what happened before that. On the other hand, not knowing everything is quite different from not knowing anything. We have some very informed thoughts. The most popular idea explaining both the expansion of the universe and uniformity of matter.
Okay. I'm gonna stop this video here because after that is the speculations, that is the thoughts. You're gonna see those you're gonna watch the entire video like at your leisure time, but this is what we do know. This is the facts that we do know. The other the other stuff, the rest of the stuff, that is 10 to the power minus 43 to 10 to the power minus 13 second. Along this time we have a lot of speculations such as the inflation theory, the string theory, and all of that stuff. But actually, from 0 to 10 to the power minus 13 seconds, we do not have hard data about this stuff. So I'm not gonna talk about those stuff because we don't have, because I personally do not believe in those things that do not have hard data. So like those stuff don't have hard data, but this stuff do. So this is the stuff that we don't. This is what we know. Okay, and that's what we don't know, and that's what we have to find out. All right. So let's get back to here. Oh, sorry. Okay, I'll go back to my slide. Yeah. So you can see here. This is a part from later on the video, that this part 10 to the power minus 36 to 10 to the power minus 13 second, this part is the part of inflation. That is, as at this part the universe has been theorized to have expanded very rapidly at near about the speed of faster than light. Okay, so again that's also speculation, and these parts are all speculations. So that's been it. That's been it. Thank you. I've actually watched the full video, and I do recommend you to watch the full video too. So yes, but okay. Now, any questions? And after that, I will end the class here, and that is officially the end of your astrophysics course. In the next class, I will have we will solve some worksheets, and in the class after that, we will have an exam on astrophysics. So yes, any questions regarding so far? Will a time come when the universe is completely cooled down? That depends on what happens to the universe's acceleration. If the acceleration continues as it is, then definitely yes, there will a time like that will definitely come, but that time will maybe come in another 13 billion years or so. So yeah, very far away. Goodbye, gamers. See you in the next episode. Yeah. Yes, there will be exams. You will have worksheets. You'll have exams. You will have it all. Okay, just because this is live class, don't think that there will be any lack of exams or worksheets. There will be worksheets, there will be exams. There will be all of it. Thank you. Keep reading the reading material, and I'll update the slide on the reading material. Go through the reading material, go through the slides, and I'll see you around. Really, St. George's Dam in China slows down the rotation of the Earth, but how? I think that will be just like to the rate of 10 to the power minus 40 or something. So that's just insignificant. It's just some like hyped up scientific data. It's not a big deal. Don't worry about it. Alright. You're a boomer. I have a test now, please. Okay, boomer. Sorry, the boomer. Okay, boomer. Well, I'm floor gang. Alright. Okay. I'll end the class here. Thank you. See you in the next class. Allah Hafiz. Bye.